Hey everybody, this is the second video on Exponential Growth and Decay, Chapter 10.1, Part 2. I want to start off this video by a little bit of a clarification or a correction. And on the last video, and I think in one of the other ones too, I found out after I watched it again that I had said that the growth was the base is greater than 0. That was just an error on my part. I think I even wrote it wrong. The base is always greater than 1 if it's growth, and the base is between 0 and 1 if it's decay. Alright, we're going to talk about this thing called radioactive decay a little bit here before we do some problems. Radioactive decay is used oftentimes in carbon dating, carbon-14 dating, and medical tests and some other things. Let's take a look at what it really means. Alright. Just by way of example, let's just talk about carbon, but this basic idea applies to every element, really. Carbon is number 6 on the table of elements, and normal carbon, I'll say normal carbon, is what's called carbon 12, and that 12 comes from the sum of protons and neutrons that are in the center of that carbon atom, and of course it's surrounded by 6 electrons. Neutrons and protons are found together, and that's called carbon 12. But life being what it is, sometimes an extra neutron gets introduced into the mix here. It acts an extra neutron, and that gives us a total of 13. And that is a fairly stable element as well. But sometimes there's another one that is added, and that makes this carbon-14. And carbon-14 is an unstable element. In other words, it doesn't like this discrepancy between the neutrons, the protons, and the electrons, because they want to have an equal number so that they're stable. Well, when something gets to be carbon-14, it's what's called radioactive. And radioactive simply means that this particular carbon is really yearning to get rid of one of those elements, or maybe both of them, that have been added unnaturally. It's a little bit like a mutation. The element's been kind of mutated because it has extra. And this occurs all the time in nature. There's always carbon-14 in the atmosphere. It doesn't mean that thing is, the carbon is going to hurt you radioactively. It's not going to, send out radioactivity and cause you to have some sort of reaction to it physically. But it means this particular element is unstable. What will happen is a little bit like what happens if you had a puddle of water. And in a puddle of water on a sunny day, the sun comes out, it beats down on that puddle of water, and what happens is that these water elements, water molecules, want to fly off and evaporate. Well, it's very similar to what happens with carbon-14. Those particular neutrons that have been added into the mix here really want to get to escape and get out into the atmosphere. And that is affected to some degree by the radioactivity in the atmosphere. And so it's desiring to get rid of that. So over time, those elements fly off of carbon-14 in the hope of returning to carbon-12 if possible, because it's more stable that way. It's like two magnets. A north pole and a south pole want to be balanced so that they have an equal, attraction to one another. But if it's out of balance, then that means that the element is unstable. So that's basically what carbon-14 is. Now, what they've used this for in dating is that if they can tell how long it's been since that particular element, that particular, say, dinosaur bone has been in the ground, based upon how long or how much carbon-14 is still left in the element compared to how much carbon-12 is there. Let's take a look at half-life. Half-life is a terminology that we use to make calculations. Let's say that an element, an object, has 100 grams of carbon or whatever, and then as that carbon-14 is flying off, in a certain period of time, it will get down to 50 grams of that carbon-14 in the particular element. So this is called half-life. When half of it is gone, we call that the half-life of the element. And then over time, half of that is gone, gets to 25 grams, and then half of that is gone, gets to 12.5 grams. This half-life is a way of measuring how long it's been. And for each element, there's a half-life of a certain number of years. So to get from here to here, this is approximately in carbon. Carbon-14 is 5,760 years. Then to get from here to here, it's another 5,760 years. And then to get to here, from here to here, another 5,760 years. So in 5,760 years, that particular element loses half of its carbon-14. And that's a way of telling, well, how long has this thing been there? So they can measure the carbon-14 in the object. So let's go ahead and do a problem with carbon-14, but this also applies to other elements like barium and some others. Barium's often used in medical testing. But let's take a look at this as a story problem here. All right, as we said, carbon-14 has a half-life of about 5,760 years. Every element has a different half-life. Some of those half-lives are in years, sometimes they're in minutes. Well, you'll see a problem on your homework where the half-life of something is actually in minutes. Well, we're going to end up using this exponential formula, y equals a e to what's called kt. And k is a constant that can be applied to this particular element, carbon-14. And we're going to go ahead and calculate what that's going to be. What is the value of k in this formula? And of course, e is just that natural number. It says to determine the constant k for carbon-14, we're going to let a be an initial amount and then put the years in here as well. Now, it doesn't really matter what number we put in here for a. We could put any number in here, 100 or 1 or 50 or whatever, but half of that in the future would be 50. Or, doesn't matter if we use 100, we could use 1,000. Half of 1,000 would be 500. Or just put 1 in there, and that's usually the easiest thing to do. Just put 1 in there, the initial amount is 1, and then in the future it will be a half. So you always find out that this a is going to be twice of what y is. So we know that the half-life of carbon is 5,760 years. So in 5,760 years, we'll have half the element left. Let's go ahead and find k. Okay, I'm going to call this 0.5. This is e to the 5760. Let's take the natural log of both sides because we have a base of e here. Natural log base e of 0.5 and the natural log base e of e to the 5760. Of course, natural log base e of e goes out and this drives around to the front and gets multiplied. Oops, I'm missing k here, aren't I? There it is. Equals 5760k. Okay, that's driven around to the front. This is now gone, natural log base e of e. And if we divide both sides by 5760, let's see what k is going to be. All right, I punched that in. Natural log base E, of course you don't see the E there, of 0.5 divided by 5760 gives us this number, and you notice that it's written in scientific notation. So we're gonna move the decimal 4 places to the left here to see what we have for a value here for this in terms of just a standard number. So if that's our number, let's go ahead and write it down. All right, once again we solved that formula for K, and we found that it was negative 0.00012. It came to us in the calculator in scientific notation. We just moved the decimal over. Then we rewrote the formula here with that K in place. Now this is the formula that can be used at any time for carbon dating. And this number, you're going to need to remember this because it's going to be in a future problem on your homework. Now also notice that this number in the exponent is a negative. The exponent's negative. That means this is decay. Because it's a negative exponent, it's decay, and that's what we're expecting here. All right, the second part of this problem would be, what if we had an item that it was a certain age? Actually, rather, if we measured how much was left in an item at a certain point, we could calculate the date. And let's do that. Let's say a woolly mammoth bones determined there was 3% of the carbon-14 was left in the item. How long ago would that have been? Well, 3%. Let's go ahead and if we put a 1 in here for A, 3% of that would be 0.03. 3% of the initial amount gives us the half-life. So if the initial amount's 1, it's 0.03. But this is what you're going to have to figure out what these numbers are. I would just call this one 1 and then put that amount that's remaining over here. So now we're left to use logarithms to calculate what t is. So I'm going to divide both sides by 1. Of course, that doesn't do anything here, so I'm just going to ignore the 1. And then let's take the natural log base e of both sides. 0.03 equals negative 0.00012t. Now, what happened to this? Well, it moved around to the front after I took the natural log of both sides. I guess I can show what just happened here. I took the natural log base e of e to the negative 0.00012t. Hopefully you've been doing this long enough, you begin to realize that this is going to go out, and this is going to roll around to the front. So, because it's getting multiplied according to the property there. Now, to get t alone, we're going to divide by negative 0.00012 on both sides. And let's find out how many years ago this particular, I guess, woolly mammoth may have lived. Let's take a look at the calculator. All right, I went ahead and stuck that calculation in there, the natural log of 0.03. Divide that by the number on the bottom, negative 0.00012. Let's see what we end up for. Oh, it says it's about 29,000 years. Approximately 29,000 years. Well, let's jot that down. $29,200 years. It tells us that that particular half-life, if it's only 3%, is left, would have been about 29,200 years or so. So this is how they calculate the years on this. By the way, just a note about carbon dating. This carbon dating is only effective up to a certain number of years. This can't be extended out forever. At some point, when this percent gets so small, it's negligible, and the amount of error that's involved in the calculation overcomes it. And it's not very long. It doesn't take, I don't know, it's probably about 35,000 years or so to where you can't really use carbon dating to calculate the date of things. Also, this sort of assumes that the radioactivity in the atmosphere, the radiation coming from the sun, is a constant, and it may not be. In fact, we get the impression that it changes over time. And so these calculations are pretty marginal at some times in making decisions on how old things live. There are other methods for calculating half-life, but this carbon dating is only useful up to about, I don't know, 35 or 45,000 years. All right, let's take a look at a different problem. All right, let's take a look at problem 13 from your homework. It's another problem about dinosaurs and so forth. One of the things they don't give you in the problem is that number. So for carbon 14, you're going to have to remember that number is negative 0.00012, or you just look back in your book and see where that is. All right, it says on problem 13 that a paleontologist finds a bone that might be a dinosaur bone. In the lab, she finds that carbon 14 found in the bone is 1/12 of that found in living bone tissue. Could this bone have belonged to a dinosaur? Well, let's go ahead and make the calculation here and see how many years that might have been. So if the initial amount was 1, the future amount was 1/12. I'll just leave that fraction in there. And we're going to use this number for K and T. Now that number, again, you had to pull that from the previous problem. It wasn't given to you. Well, let's do the same thing we did before. Divide both sides by 1, which is immaterial. Let's take the natural log base E of 1/12. That's equal to the natural log base E of E to the negative 0.00012t. First, the natural log goes out. This is natural log base E of 1/12. This is out. That around the front, negative 0.00012t, and then dividing by negative 0.00012. So this problem is just like the one I did in the past here, but I just wanted to remind you that number, you had to pull that from the previous problem. Let's make the calculation. All right, I did that calculation. So make sure that you close your parentheses here. If you don't close the parentheses, you will definitely get the wrong answer there. See, I've closed these parentheses right here, and that allows me to make sure that I'm not dividing the thing inside the result there. So with our calculation here, again, make sure you close the parentheses here, we end up with this being about 20,708. Now, by the way, these numbers that we put up here, they're estimates. This is just kind of close, so you could probably round this off to 20,000. You don't need to be that accurate, certainly not to the decimal place. But that basically says that this bone that they found was 20,000 years ago. Now again, there's error involved in all of this, and carbon 14 is dependent on how much radiation is coming in from the atmosphere. So technically, this is probably, from what we seem to in all the discussions, dinosaurs are supposed to have died out about 63 million years ago. So this isn't even in the neighborhood. And of course, this again is assuming that all of these calculations are not affected by radiation in the atmosphere and so forth. All right, let's take a look at another one. All right, let's just take a look at a couple of problems that are. We're not going to do them all for you, but just to talk about a couple things. Problem number 15 talks about bacteria dividing, forming two bacteria. So if it divides and forms two, you start with one and it becomes two. This is the way you'd probably think about that. Bacteria is dividing and becoming two. And it says that it divides in every 20 minutes. So if we let the time be 20, and remember this is in minutes now, so you go ahead and calculate K, doing the same thing we've been doing, to come up with the formula. Make sure you write the formula in the end in this particular form. Y equals A e to whatever you come up with for K times T. Okay, so just go ahead and you can do 15 on your own there. All right, let's take a look at problem 17. I'm not going to do the whole thing for you here, but I want to talk about a couple things. Problem 17 says the annual gross domestic product of a country is the value of all of the goods and services produced in the country during a year. During the period of 1985 to 1999, the gross domestic product of the U.S. grew about 3.2%. 3.2% growth during that particular period of time, okay, measured in 1996 dollars. In 1985, it says that the GDP was 5,717 billion. Okay, make sure that you know how many zeros that's going to be or so when you're calculating this in terms of billion. Now, if you can tell from the formulas that we used and were given to you on the last video, since this has a percent in the problem, we're going to make this calculation using the other formula, and that was the one, A1 plus R raised to the T. Now again, remember this plus sign means it's gross. If this was a minus sign, this would be decay. Well, in 1985, we're going to call that year 0. And we do that so that we can use this number as our initial amount. So y equals 5717 is the initial amount. And the interest rate is 3.2%. Make sure you get the right number of decimal places here. Move the decimal 2 places. 3.2% times T. So there's your formula, and this particular formula is asking for, on problem 17, assume this rate of growth continues, what will the GDP be in 2010? Well, in the year 2010, that is 15 plus 10 is 25 years. That's the 25th year. So you're going to take that and stick that in there and go ahead and calculate the GDP in that year. And then problem 18 is similar to that, but you're going to work backwards and you're going to have to find T if you're given this Y. So problem 18, you're going to be given Y, but you're going to need to find T. I'll let you go ahead and do those two problems. All right, problem number 19 is an interesting problem because they've actually given us two different formulas here, or two different calculations we have to make. The problem basically says in the end, if the rates continue, when will the women's winning high jump be higher than the men's? Notice we're comparing two things, the women and the men. And if you can use the formula that's necessary, of course this one had percent in it, so you're going to use the formula 1 plus R because it's growth. And again, the same thing over here, 1 plus R, and it's growth as well. You want to calculate both of these. You could do that and then compare them and see when they're the same. But really what you really need to do is set both of them up, the women's and the men's. They're going to give you an initial amount and they give you a rate. Give you an initial amount and a rate. And since they want to find out when one's going to pass the other, one of these is going to be passed. We're basically finding out where do they cross. So just set them equal to each other. Set this part equal to this part and solve the system. Now there's a couple of really slick techniques that you can use, but I'll show you that at another time. All right, so to go ahead and calculate what year that would be that these rates would be the same. You're going to basically solve a system here. All right, let's you do that one. All right, let's go ahead and tackle problem 20 here. It says the Mendez family bought a new home 10 years ago for $120,000. Okay, and this was 10 years ago. Okay, the house is now worth $191,000. So over time, it started here and then it's moving to $191,000. Assume a steady rate of growth. What was the yearly rate of appreciation? Well, here they did not give us the rate in percent, but we need to find that. So we're going to use this formula that has the percent in it. And anytime the percent is given or requested, you're going to end up using this formula. And of course it grew, so that should be a plus sign here. It grew from here to here. If we let this be year 0, 120,000, and then another 91 to be 10 years later. So we're going to put this in for your initial amount. So that would be 120,000 is what the first thing that happened in time. We don't know the rate, but we do know that in 10 years the amount was 191,000. So here's a problem where you're actually asked to find R. Now, the first time I looked at this, I thought, oh, I'm going to have to use logs. No, we don't need logs. Why is that? Well, because the variable we're trying to find is not up in the exponent. So this problem does not involve using logs. Let's go ahead and solve it. Dividing both sides by the 120,000. Of course, this is going to go out. Let's cancel the zeros here. This is 191 over 120. And this is 1 plus r raised to the 10. Now, if I want to get r alone, well, what's been done to r? Well, 1's been added, then it's been raised to the 10th power. So if I'm going to take if I'm going to do the undo operation, I'd have to do the opposite, or the inverse, of raising it to the 10th power, and that would be taking the 10th root of it. I'm going to use fractional exponents to do that. Take it to the 1/10th power. 10, the power of 10 and the power of 1/10, when we multiply them together, they become 1 and undo each other. So let's multiply both sides, or take both sides to the 10th power. These two are going to go out. We get 191 over 120 raised to the 1/10th power equals 1 plus r. Those two undid each other. Now, if we simply subtract 1 from both sides, we should end up with our answer. So I'm out of room here, but let's go over here and find out that r is equal to this whole thing minus 1. Let's go ahead and put that in the calculator. All right, I went ahead and punched this in the calculator. One thing I forgot to mention here was that I just went ahead and divided both of these numbers by 1,000 to get the numbers a little smaller, less to work with. And I'm raising the whole thing. Make sure you use parentheses here to the 1/10th power. Make sure you get out from underneath that, or out from underneath that exponent there, and then you can subtract 1. Let's see what we end up with here. We get an amount of 0.04758. Now what is that? Well, this is a rate. This is a percentage. It turns out to be, move the decimal 2 places, it's about 4.8%. So let's jot that down. All right, so this is the number we got in the calculator. Remember, you were calculating the rate of growth, and so it went up about 4.8%. I moved the decimal 2 places. So that shows the appreciation. What we find from all of these problems is that no matter where the variable is, you can always solve for it if you do the undo operations. Try to think about that when you go to start the problem, because like I did, I thought, oh, I'm going to have to use logs to solve this one, but the variable was not in the exponent. So I have to, what's been done to r, and it clearly then tells you how it is you're supposed to solve the problem. This is an important thing to think about every time you go to solve an equation. So let's take a look at the homework for tonight. All right. here's the assignment for tonight and for tomorrow. I'm not going to show a video here. If you have a question about any of these problems, please send me an email and let me know which problems you're concerned about, and I'll get back to you right away as soon as possible. I want to make a note of a couple things here. Problem 24 on this page 563. You may have to just go ahead and put those equations in your calculator to answer that question. Put those in your calculator in the y equals screen. You're going to have 4 of them: y1, y2, y3, y4. Put all of them in there and see which one of them matches the picture. Just go ahead and put them in your calculator to do that. The other thing I need to mention here is if you're using the answers, the solutions that are online, occasionally you'll find that those answers out there, they're using a different technique than I've been using. I think there's a couple of problems on the practice test where they're using different technique to solve those, and it's a little bit odd. For example, on practice test numbers 23 and number 24, if you look at the solutions that they give you on those on the line, they're done in a different way. Just try to go back and do it the way we've done it in the past. Well, this brings us to the end of this chapter on exponentials and logarithms. You're going to have a vacation next week, take off that spring break, and the week after we're going to go ahead and start chapter 9. So make sure you get caught up here so we can move on fresh starting in a week from Monday. So take a week off here if you need to catch up. You'll be home anyway probably. You can catch up if you want to on your vacation time if you'd like. But we need to keep moving, and it is important to remember that this material is going to be, even though you may not be testing on it and getting a grade on it, you are going to need this information for the future. So try not to just forget about this stuff, even though, oh, I'm not going to be tested on it. In reality, there is a test on it, and it's life. So just being able to move on wherever you go next year, pre-calculus or wherever you're headed. So exponential functions are some of the most important things that we do in making calculations in the real world. So have a good week. If you have a question, please send me an email. I'll get back to you as soon as I can. Oh, by the way, also make sure you visit that that solutions out in your book, and also check out subscribing to my videos out there on Crazy Scout. All right, we'll talk to you later.